Hey there, determining linear factors of quadratic polynomials with real coefficients. So hopefully you've watched my previous video, and previously we looked at the thing called the conjugate root theorem, or the complex conjugate root theorem, to give it its full name there, because it uses the complex conjugate. That's amazing. So basically we saw last time that polynomials, quadratic polynomials in this case, always have two roots. When we have a case of where the discriminant is less than 0, it's negative, we have two complex roots which are conjugates of each other. So we can do that to determine linear factors and create the quadratic polynomial where the roots came from. So in other words, this is the reverse of the previous video. So as an example, determine the equation of the quadratic polynomial p of z with real coefficients, which is important. It's got real coefficients, and we are given some information that negative 11 plus 2i is a root or a solution of the quadratic. So given that negative 11 plus 2i is a root of the quadratic, just to give it a name, I'll just call it alpha or something like that. The conjugate root theorem, or the complex conjugate root theorem, says negative 11 minus 2i is also a root. Let's just call that beta or beta. Now, if we think about what we've done with quadratics before, and things like the null factor law, so we would see things now, you might have seen things in terms of x before, or z. Works the same way, okay? Z suggests complex numbers, but we can use x as the pronumeral, no problem at all. But anyway, either way, you might remember when we break down each of the roots or each of the factors and they're equal to 0, you would get, as an example, something like x minus 5 equals 0, so therefore one of the roots would be 5. If you had x plus 2 equals 0, one of the roots, one of the solutions would be x equals negative 2. So it's an x minus, alright, so x, if it's a positive 5, it's x minus 5, a minus there. That's minus a negative, you see, so you get a negative root, or if you have a negative root, it's x minus negative 2 or x plus 2. Alright, so in this case with z, we have a z minus. Now the first root, alpha up there, negative 11 plus 2i. Now that equals 0 because it's null factor law, and that could be then used to determine the root which was given above, but it's a factor as it sits there. It's one of the two factors for this this quadratic. Okay, we could write that as z plus, because it's minus negative 11, z plus 11 minus 2i if we like. Likewise, okay, using the null factor law, we could also see for beta, okay, we have z minus negative 11 minus 2i, and if you like, you could write as z plus 11 plus 2i. So if we're going to determine an equation, we have to multiply the two factors together, so we have z plus 11 minus 2i by z plus 11 plus 2i. Now if you notice something pretty freaky here, we have a z plus 11 all squared. Okay, if we have a look at that, we've got z plus 11, z plus 11, z plus 11 all squared. Alternately, we could look at it as a plus b, a minus b, which is the difference of two squares. So there's the plus b minus b part, and there's the minus, there's the plus. So it'd be a squared. So a plus ba minus b is a squared minus b squared. Like so. So if we want expanded form, we have z squared plus 22z plus 121. So that's perfect square expansion, yet another identity. And whoops, that should have been a square there in the previous line. Minus 4i squared. So we have z squared plus 22z plus 121. That's 22z, by the way. Got to be careful to make sure our 2's and our z's are distinct. 121. Now I squared is negative 1. Negative 1 times that. Negative 1 is positive 1, so plus 4. And simplifying that, z squared plus 22z plus 125. So we've determined our polynomial, okay? And if it was in terms of x, same deal, alright? That would be our answer. Alright, one more. Okay, so we've got a situation, b and c are real numbers, okay? So we have a quadratic equation. This one's in terms of z as well, but remember it can be in terms of x, no problem. So it's a monic, and we have z squared plus bz plus c equals 0. Again, real numbers means we're fine to keep going as we have been going, because we've been operating under real coefficients. Okay, we're given some information here that might be helpful. We're given the solutions or the roots. Z equals 2 minus 3i, z equals 2 plus 3i. Notice how they're complex conjugates of each other. Alright, we have to determine what b and c are. Okay, a little bit of similarity to the previous example. We've got two factors. Now, same process as we just did in the previous question here. So we have z minus 2 minus negative 3i, which is z minus 2 plus 3i. And we have z minus 2 minus 3i would be z minus z minus 2 minus 3i would have a factor of z equals 2 plus 3i, because z minus, looking at this one for example, 2 plus 3i is z minus 2 minus 3i. Okay, so that's the factor there. Whereas this other one, we can, okay, we can follow that crazy path there. But if we have the factor z minus that factor in the brackets 2, we've got, that's 2 minus 3i. So we have z minus 2 minus a negative, which is plus 3i. Okay, so you can see z minus 2 plus 3i and z minus 2 minus 2i. And then we could expand this out, but did you notice last time that I used the perfect square? Okay, perfect square expansion, much more efficient way of doing it. It fast tracks the FOIL with 6 terms. Forget about it. So we have, if we let the first thing there be the A, and then we let the second thing be the B, we have A plus B, A minus B is A squared minus B squared, which is what that is. There's your minus, and there's your A squared, and there's your B squared. Okay, so then we use a perfect square expansion. Actually, before, did I say, sorry, that was the perfect one. I've ironically made a imperfect statement there. There's your perfect square expansion there. Okay, that is the difference of two squares. Sorry, late at night, what am I going to do? A plus b, a minus b is a squared minus b squared, difference of two squares. Alright, a plus b, a minus b, difference of two squares, those being the two squares. However, one of the squares is itself a perfect square, so sorry about that. So we have z squared minus 2 times negative 2z is minus 4z, negative 2 times negative 2 is positive 4. The 3i squared is negative 1, squaring the 3 gives you 9, so we get z squared minus 4z plus 13. Therefore, to answer the question, b would have to be the real number negative 4 and c would have to be the real number 13.